Bismillahirrahmanirrahim. I am Rashida here with one of the most important topic of UV spectroscopy. So today I am going to deliver my lecture on the lambda max calculations in dynes using Woodward Fisher rules. Okay, in the first part of our presentation. We will try to understand what type of rules are called Woodward-Fisher rules. So, in 1945, Robert Burns Woodward gave certain rules for correlating lambda max with molecular structure, and in 1959, Louis Frederick Fisher modified these rules with more experimental data, and such modified rules are known as Woodward-Fisher rules. Now, what is the application of this rule? So, this rule is used to calculate the position and lambda max for a given structure by relating the position and degree of substitutions of chromophore. Now, what is lambda max? The wavelength at which a substance has its strongest photon absorption is known as lambda max, and we know that all the conjugated systems have a particular value of lambda max, which is also known as base value or parent value. Okay, in this lecture we will focus dyne compounds, as I already mentioned in the first part of presentation. In this lecture we will only discuss the dyne compounds. So, what type of compounds are called dyne compounds? So, dyne compounds are the class of unsaturated hydrocarbons that contain two conjugated carbon-carbon double bonds. You can see in the examples. In the example A, I have a single member ring with two conjugated carbon-carbon double bonds, and the presence of these two conjugated carbon double bonds shows that the compound is dyne. On the other hand, I have a fused form of the ring, and this ring again containing two conjugated carbon-carbon double bonds. So the presence of these two conjugated carbon-carbon bonds shows that such kind of compounds are called dynes. Now, classification of dynes. Dynes are classified as acyclic dynes and the cyclic dynes, and cyclic and acyclic dynes examples are given. You can see. Okay, we have further types of cyclic dynes. The first type of cyclic dyne is homoallunar dyne, and the second type is heteroallunar dyne. What type of dynes are called homoallunar dyne, and why they are called homoallunar dyne? So the cyclic dynes having conjugated double bond in the same ring means these are the dynes that contain a conjugated double bonds in the same ring. This is why they are called homoallunar dyne, and the base value for homoallunar dyne is 253 nanometer. You can see the example. I have a simple ring, 6-member ring that is containing two conjugated carbon-carbon double bonds, and these double bonds are present in the same ring. This is why they are called homoallunar dyne. Now the second type is heteroallunar dyne. Heteroallunar dynes are the cyclic dynes having conjugated double bonds in different rings, and the base value for heteroallunar dyne is 214 nanometer. And you can see the example that I have a fused form of the ring, and this fused form of the ring is also containing the two conjugated carbon-carbon double bonds, but these conjugated double bonds are not present in the same ring. This is why it is known as heteroallunar dyne. Okay, now we have to understand some terminologies to solve the problems related to lambda max. Let's go through those terminologies. So the first is about S-cis or cissoid. If two double bonds are present on the same side of single ring, they are called cissoids. And the second terminology is about S-trans or transoid. So what type of compounds are called transoid? If two double bonds are present on the opposite side of the single ring, such kind of compounds are called transoids. You can see in the example, one, the first example I have mentioned, this is cissoid compound, because the two double bonds are on the same side of the single bond. On the other hand, on the right side of this slide, you can see I have shown the transoids because the two double bonds are on the opposite side of the single bond. Okay, now the next terminology is about the double bond extending conjugation. What is the double bond extending conjugation? So in a conjugated diene, there are two double bonds, and if it has one more double bond in conjugation other than the two, this addition of double bond is known as double bond extending conjugation. Okay, let's consider the example of such a compound containing the double bond extending conjugation. You can see in the molecule that it consists of a conjugated carbon-carbon double bonds, and other than these two conjugated carbon-carbon double bond, there is a third double bond which is known as double bond extending conjugation, because it is extending the conjugation of the compound. This is why it is called double bond extending conjugation. So the next terminology is alkyl substituents or the ring residues. Okay, in the first example, you can say the two hydrogen atoms of the conjugated system are displaced by two ring residues. And in the second example, you can see that there are two ring residues and also a methyl group is attached to the ring. Okay, now we are going to talk about the next terminology that affect the lambda max of the dienes is about the endocyclic double bonds. What type of bonds are called endocyclic double bonds? So the double bonds present in a ring, yani those double bonds which are present inside the ring, they are called endocyclic double bonds. And you can see in the example there is a ring that is containing the double bond inside the ring. Such kind of compounds are called endocyclic double bond, not a diene. I'm talking about just endocyclic double bond. Okay, and the second terminology is exocyclic double bond. In the exocyclic double bond, you can see the double bond in which one of the doubly bonded atom is a part of a ring. Means if the other if a ring is also, if a double bond is present at the corner of the other ring, then it is considered corner or the outside of the ring, it is considered as the exocyclic double bond. You can see the example. I have two fused rings, ring A and B, and the the double bond B, double bond B is the double bond in the ring B is considered as exocyclic double bond of ring A. But in this compound, you can see there is no exocyclic double bond for the for B molecule. There is a exocyclic double bond only for the A molecule because of the this double bond present in the corner of A molecule ring. Okay, now we are going to move towards the next part of our presentation, that is about the parent values or the base values and the increments for different substitutions or the group. This is the most important part of our presentation because knowing about these values, we will be able to find the lambda max of dienes. Okay. So the first important part is conjugated dienes correlations. So the base value for an unsubstituted conjugated homoallylar diene is 253 nanometer, as I already mentioned in the first part of my presentation. And the second important thing is that the base value for unsubstituted conjugated acyclic or heteroallylar diene is 214 nanometer. And what are the increments? The first increment is that each if there is an extra double bond in conjugation, then we have to add plus 30 nanometer. And if I have an exocyclic double bond, then I have to add 5 And if there is a substituent effect in the diene molecule, then we have to add different values on the basis of the functional group or the substituent attached to the ring. For example, I have the ester group. If I have a ester group attached to the diene molecule, then I have to add 0. There will be no any addition in this case. But if I have a simple alkyl substituents or the rings residues in the ring residues in the diene, then I have to 8 plus 5. And if I have halogen, for example Cl or Br in the ring, then I have to 8 5 again. And if I have OR group present in the diene, then I have to 8 plus 6 nanometer in order to calculate the lambda max overall value. Okay, now we will move towards our practical work by calculating the lambda max. Okay, here I have taken different examples of the molecule or the dienes and in which we are going to calculate the lambda max. So the first molecule, you can say the base value is the molecule is as the molecule base value is 214 nanometer. And it is containing 3 ring residues. I have mentioned there 1, 2 and 3, and this is why I have 8 plus 15 because the each ring residues contain 5, so 3 multiplied 5 is equal to 15. And I have also a alkyl substituent in the diene and presented by the sample A. And because of the presence of this alkyl substituent, I have to 8 plus 5. And you can see there is a exocyclic carbon-carbon double bond. There is an exocyclic carbon-carbon double bond. Therefore, I have to 8 plus 5 again. After the total of these additions, I will get the lambda max for this molecule. And the total lambda max is 239 nanometer. Okay, now I have another example of a molecule that you can say this is a homoallylar molecule. Why it is homoallylar molecule? You can say both the double bonds are present in the same ring. This is why it is called homoallylar diene. And this and we know that the base value for homoallylar diene is 253 nanometer. And you can say 3 ring residues I have represented by the numbers that 1 2 3. There are 3 ring residues, so I have to multiply these 3 by 5 and I will get 15. Then you can see I have one exo carbon double bond in the ring, so I have to 8 again plus 5, so the total lambda max is 273 nanometer. I have another compound, the base value again it is a heteroallylar molecule or the diene, therefore its base value is 253 nanometer. Again there are 3 ring residues, therefore I have to add plus 15. And I have one exocyclic carbon-carbon double bond, again add 5. And again there is a new point we have to note in this molecule is that there is a double bond extending conjugation in this diene molecule. You can see although I have 2 conjugated carbon-carbon double bonds, in addition to these 2 conjugated carbon-carbon double bonds, I have a third double bond as well. This is why I have to add plus 30 if I have a double bond extending conjugation and the diene. So the total lambda max is 303 nanometer. Now let's consider another molecule. So the lambda max for such a molecule such molecule is 214 nanometer. And you can see there are two ring residues I have mentioned in red color. So I have to 8 plus 10 because each ring residue is carrying 5. So if I have two ring residues, then I have to multiply 2 by 5 with 5, so I will get 10. Then you can see I have exocyclic carbon-carbon double bond again at 5. So the total lambda max for this diene is 229 nanometer. Okay, now I have another diene molecule, or the transoid, and the base value for this diene is 214 nanometer. And again you can see that the 5 ring residues, there are 5 ring residues, so I have to multiply 5 by 5, so I will get 25. And one extra double bond is also present, so I have to add 30. And then I have 3 exocyclic carbon-carbon double bonds, again I have to add 15, so the total lambda max is 284 nanometer. Now another molecule of a diene compound. So this is a cis-oid number diene, and it lambda max is 253 nanometer. There are 3 ring residues, so total 15. And one alkyl substituent is also present, so I have to add 5. One exocyclic carbon-carbon bond is present, again I have to add 5. So the total lambda max for this diene is 278 nanometer. So this is all about my today's lecture. Thank you so very much.